morning children, and welcome back to your chemistry class. So we had already finished with the D block elements. Today we shall start with the F block elements. Now these F block elements, they are also called as inner transition elements, right? So the elements in which the last electron, it enters the F orbital, okay, of the atoms, they are termed as F block elements. They are also called as inner transition elements. They consist of two series. What are those two series we are talking about over here? One is your lanthanoid series and the other one is your actinoid series, right? And the general electronic configuration for your F block element is what? It is N-2 F, where the electron ranges over here from 1 to 14, then N-1 D, where the electron ranges from 0 to 1, NS2. This is the electronic configuration which is found in the F block elements, right? Now lanthanoids, the elements in which the last electron, it enters one of the 4f orbital, then it is called as your lanthanide series, right? Or lanthanoids or lanthanols, whatever you can call it. And there are about 14 elements which are present in this series. How many elements are present in lanthanoid? There are 14 elements present in this series. And this series, the lanthanoid series, it starts from lanthanium to cerium and it goes till lutetium, okay? Lutetium. So the cerium atomic number is 58. It starts from 58, and lutetium, the atomic number is 71, right? And these are also called as rare earth elements. What are they called as? They are the rare earth elements, right? Now let's talk something about actinoids. These actinoids, the last electron, it enters into the 5f orbital. The last electron enters where? In the 5f orbitals, right? And they are called as actinides or actinoids. And they also include how many electrons present here? There are 14 elements present in this actinoid series, okay? 14 elements are present here. Fine. And it starts from what? Actinium is the first member, followed by thorium, whose atomic number is 90, and it goes to lawrencium, right? Lawrencium is Lr, whose atomic number is 103. So this was about actinoids. Now this much is enough for actinoids. Actinoids in your 2021 syllabus has been removed. Only the introduction to actinoid is there. Now what we have to study is more about the properties of lanthanoid, that we are going to start now. So let us begin firstly with the general electronic configuration of lanthanoid series. So over here, these F block elements, as you already know, there are how many elements present over here? 14 elements. And the general electronic configuration is what? Xenon 4f, where F ranges from 1 to 14. The electrons in F orbital, they range from 1 to 14. 5d, where over here electron range from 0 to 1, and 6s2, okay? Now the lanthanoids, they have electronic configuration with 6s2 filled, and the gradual filling of what are you going to see? 4f orbital. But due to similar energies of 4f and 5d orbitals, the order of filling of the 4f orbitals, they are quite irregular. Clear? So for example, like lanthanum, its configuration will go like this, that is xenon 4f0 5d1 6s2, but there is a successive filling of the electrons that you see in the 4f electronic configuration. Europium with your atomic number 63, where we will find xenon 4f7 5d0 6s2, right? So over here you will see that lanthanum, the atomic number is 57, and that of uranium, it is 63, right? So what did we see over here? What did I tell you? That with the 4f and 5d orbitals, the filling of the electron with the 4f orbital is quite irregular. Why so? Because of the similar energies which are found in the 4f and 5d orbitals. So this is what you can see. Now let us see the electronic configuration of cerium, whose atomic number is 58. So let's check this particular element and see the configuration. It is 4f2 5d0 6s2. So if you compare it with 57 and 58, right? So over here, see, it is 4f0, here it becomes 4f2, 5d1, and it has become 5d0 and 6s2, right? Similarly, if you see the configuration of ytterbium, whose atomic number is 70, right? And if we configure this, we get xenon 4f14 6s2. So over here, what did we see? That filling of the 4f orbital is absolutely irregular, right? First, if you check 57, it is 4f0, 58 4f2, 63 4f7, and if it comes to 70, there is no d orbital. It is the 4f is completely filled with there is no d orbital over here, and it straight away goes to 6s2. So this was the general characteristic where you are going to use this general electronic configuration, right? Now let's talk about the second point, that is the oxidation states. So what do we know about the oxidation states? The lanthanoids, they always exhibit a very common oxidation number, that is +3. So in aqueous solution and in the solid state, this +3 oxidation state is very stable than the other two oxidation states, that is +2 and +4. They are not stable, okay. This is the most stable oxidation state. What did I say? In aqueous solution and in solid state, the +3 oxidation state is more stable than +2 and +4. Why is it so? Because the sum of the oxidation and the lattice energies of this tripositive ion is more negative as compared to +2 and +4 ions, right? So the main oxidation state of lanthanoids is what? +3. Clear? Then we next come to atomic and ionic radii. The third point is atomic and ionic radii. So over here we should know that the atomic and the ionic radii, it decreases from lanthanum to lutetium, right? And this is the unique property of lanthanoids, and this is shown because of lanthanoid contraction. Now, what is lanthanoid contraction is what we are going to understand over here. Now, moving from lanthanum to lutetium, the size of the atoms and the ions, they always decreases regularly, right? So, the 4f orbitals containing electrons, they are too diffused to screen the nucleus as effectively as the more localized inner shell. Hence, the attraction of the nucleus for the outermost electron increases, and this increases the atomic. This also happens due to increase in the atomic number. Thus, due to the imperfect shielding of your 4f orbitals, the contraction in the electron cloud of the 4f subshell increases, and therefore they show lanthanoid contraction. I hope this is very clear to you. I repeat once again that as we move along from lanthanum to lutetium, what do we see? The nuclear charge is increasing with the atomic number, with the addition of different electrons in the inner 4f orbital, right? However, remember, the 4f electrons, they shield each other from the nuclear charge imperfectly or poorly due to diffused shapes of your f orbitals. So this also causes the regular contraction in the size of the lanthanoids. Thus, the sum of the successive contraction, it gives the total lanthanoid decrease, and hence we say that lanthanoid series, they show contraction, which is also termed as lanthanoid contraction. Then fourth point, let's talk about the radioactive nature. Radioactive nature. What do we know about the radioactive nature? This chemistry of lanthanoid, it is dominated by which oxidation state? +3 oxidation state. So promethium is effectively man-made element of this lanthanoid series, whose all isotopes, they are radioactive with half-lives shorter than even 20 years. Okay, so we have the radioactive nature due to the dominance of +3 oxidation states. Then next we talk about the formation of colored compounds. Do we find colored compounds in lanthanoids? The several M3 plus lanthanoid ions, they are colored solid state, right? They are colored solids. Fine. As well as they also are colored in the aqueous solution, obviously. So color of the compounds of members of this series, it is due to what? The FF electronic transition, as F subshells, they are partly filled. So what is the reason? Reason I am writing over here. It is due to FF electronic transition, as F subshells, they are partially filled, right? Now next we talk about the complex formation. Let's talk about the complex formation. So what do we know over here? They have very less tendency to form complexes, right? Less tendency to form complexes. And why? This is because of the low charge density. Okay, because of low charge density, right? That is, I'm over here talking about the charge to size ratio. So they form complexes with the strong chelating agents like your EDTA, or it could be your oxime, etc. So no complexes with the pi bonding ligands are known up till now. And last but not the least, we talk about the alloy formation. What do we know about the alloy formation? Do they take part in the alloy formation? An alloy of lanthanide metal. Do you know what it is called as? It is called as mish metal. What it is called as? Mish metal. It has lanthanoid metal, which is lanthanoid metal is 95% present over here, and iron is 5% present over here, with traces of your sulfur, carbon, calcium, aluminium. They are also present, and this is used in the production of bullets and shells and the lighter flints. Okay, so these mixed oxides of lanthanides, they are also used as catalysts in the petroleum cracking. So what is the alloy formation or the alloy of lanthanide metal called as mish metal, which is made by lanthanide metal, which is 95%, iron is 5% with certain traces. And where are they used? They are used for the production of the bullets and the shells and even the lighter flints. And even the mixed oxides of the lanthanides, they are used as the catalysts in the petroleum cracking. Right? So with this, we finish off with the chapter of your D and F block elements. Thank you.